Okay, yet another review video. Let's see, what have I done? There we go, that's a little bit better. This is all about reviewing for tests. This is actually covering test one that we did earlier this semester. Never really went over it in class, not in detail anyways. And as we review, or as a review for the final, as you review for the final, I thought I should do that. So let's do that. I'll be specifically using test 1B. There were two tests, test 1A, test 1B. They're very similar. You can expect some similar problems to this on the final. And I'll also post the key that I've written up here to go with it online on the class website on our Blackboard site. So let's start with the first problem. The one that has to deal with the op-amp problem, and it says use a difference amplifier. At least on this test it did. On the other test I think it said use a summing amp. And there were a couple of typos on the when we wrote up the test. Professor Vickus and I were tossing back and forth ideas, and unfortunately we did blow this one a little bit, but I remember grading it was made a great joy by virtue of that. That is to say, I did take that into account when I graded the tests. I was always trying to err on the side of the students. Now, look, the numbers are 1 volt, 4.4. All right, these are in volts, of course. And we got -1 and 4.4. And then we had 1 and 1.8. We're going to mix that for a second. And then we have 2 and 11. So yeah, I see that the light's getting in the way, but I'll just tell you, this is V in, this is V out, -1, 4.4, 1, 1.8, 2, and 11. And we're going to mix this because actually it's kind of stupid to not have seen that, I suppose. If you watch this, I mean, if we plot this out, you go to -1, you go 1, and you go 2. And at 2, we're up someplace at 11. And at 1, we're at someplace like 1.8. And at -1, we're up at 4.4. That's not exactly aligned. It doesn't work. So we're going to mix this middle point. All right. Now, the reason that we have this data, of course, is what we're trying to do is we're trying to say, I mean, the problem here says, you are to design a difference amplifier circuit that will convert the input values to the output values in the table on the right. What I'm trying to test you on, and evaluate you with, I guess, is your utilization of either summing amp or difference amp, or both, to convert input out data to output data. And this goes right into lab number 2, where you have the potentiometer that had a non-zero offset. When it was pointing at 0 degrees, it had a non-zero voltage. So that was offset there. It's checking Java update available. Let's see what that is. So there's a practical reason for removing an offset. There's also a practical reason for changing the gain or changing the relationship. So first we have to determine what we want out of this. If these are the input voltages and these are the output voltages, then what we do is we actually plot output as a function of input. Or what we could say is, look, let's look at delta V out. Okay, from this point to that point, we have 11 minus 4.4. Delta V out is 6.6 volts. Okay, over the same, and that's going from a V in of -1 up to 2. So we have delta V in, that is to say that produce that delta V out, or they will be producing that, is going to be 2 minus a -1 is 3 volts. And so what we can do is we can actually divide the 6.6 by the 3 and say that's equal to the gain. The gain is the change in the output voltage for the change in input voltage. And so that's going to be 6.6 divided by 3 is equal to 2.2. That's the gain of the circuit. Okay, that's the first thing. Now, we do a standard slope-intercept form to come up with the equation. Now, that'll give us the offset voltage, but it doesn't necessarily give us, as a matter of fact, it very rarely gives us the voltage that we need to add or subtract to our input. And I'll show that to you now. What I'm saying by that is, if we do this in the form V out, otherwise known as Y, is equal to Mx, otherwise known as G times V in. So we have 2.2, that's our gain, times V in, plus, and I'll call it beta. Y is equal to Mx plus B, V out is equal to 2.2 V in plus beta, for example. So if we do that, now we can actually select some data points and plug them in. So for example, if I have an 11 volt output, 11 volts, let's just even leave off the, or maybe I'll make, yeah, I guess I'll put the volts in. 11 volts is equal to 2.2 times the input voltage, which is 2 volts, plus beta. In other words, beta is equal to 6.6 volts. Kind of a coincidence with what we had up above, but that's okay. 11 minus 2.2 times 2 is 4.4. 11 minus 4.4 is 6.6. So the relationship now is V out is equal to 2.2 Vn plus 6.6 volts. Now a couple of things occur here. First off, we have a gain of positive 2.2. It means we cannot do this with a summing amp. You've got a positive gain, you've got to use a difference amplifier, which is why that screwed up the next part of the problem. Now, what else do we have here? You're not going to multiply 2.2 times Vn. Okay, you could do that with a non-inverting amplifier, actually. 1 plus R2 over R1 is equal to 2.2, so you have 1 plus 1.2 being R2 over R1. So we can do that. But then when we add a 6.6 volt offset to it, we either have to have a difference amplifier adding a negative 6.6 to this function, or we have to have, well, we could do it with a summing amplifier. But there's a way we can accomplish this in one single step. And the way we do that, and this is where the difference amps and the summing amps come into play, V out is actually equal to 2.2 times Vn minus V minus 3. I'm having a hard time writing that. I guess I'll just do this. Minus 3 volts. All right? If you run through the mathematics of that, of course, 2.2 Vn, 2.2 Vn, we got that. 2.2 times a negative of a negative, that means 2.2 times 3 is 6 volts. So good. What we've done here is cast this, and maybe I'll make these as brackets instead of parentheses, demonstrate that 2.2 is applied to this entire function on the inside. That's a difference amplifier. That's what a difference amplifier does. Let's go ahead and draw it out. So again, though, to recap and to bore you, take the input-output relationship, figure out your delta V out and your delta V in, figure out the gain. Plug that into a linear equation, figure out the offset, and then cast it in the form of either a summing amp or a difference amp, depending upon what you're trying to accomplish. In this case, we've got it cast as a difference amp because it's the only choice available to us with a positive gain. Now, I'll try to address that in the next problem. Having said that, now that we've got this relationship, how do we do that in an op-amp circuit? So V out is equal to 2.2 times Vn minus a minus 3. Well, what the difference amp is, we'll draw our difference amp first. Make the minus on top and the plus on the bottom. Plus 12 volts, minus 12 volts. We have R2 and R1, if you want to look at it that way, R2, R1. And up here, we've got the same R2 and R1. They have to have the same ratio. And for us, in this problem, R2 over R1 is equal to 2.2. And so let's go ahead and say that's a 22K resistor over a 10K resistor. So make this one equal to 22K. That one's equal to 10K up above. This is equal to 10K. And this is 22K up above like that. Now, this is going to be the voltage that comes through positively. This is the voltage that's going to be subtracted. Right now we're subtracting the negative 3. We need to generate a negative 3 over here. Plus 12 volts. Let me make it a little lower because I know that the light might be getting in the way there. I'll try to do better on the next one. Sorry about the reflection. Yeah, I don't have anything I can put the tablet on top of for now. So let's see, we put our load follower down here, minus plus. I'm going to take the output of the voltage of the load follower and put it right in up there. That's plus 12 volts, that's minus 12 volts. All right, we need to have those. The input to the load follower is simply coming in on the plus side. There is no connection to ground, anything like that. This is coming off of a potentiometer, which will also be tied into ground. And because it needs to give us a negative 3 volt, that's what we're going to, negative 3 volts, that's what we're subtracting. We need to tie the positive into the minus 12 volts. And I indicate there's a minus 3 volt, but we dialed this in with a screwdriver to get us a minus 3 volts. Pull this through, we're subtracting the negative 3 volts from this input. All that V in plus and minus, the V in plus goes up here, the V in minus goes down to ground like that. And over here we have a similar situation as far as V out, plus, minus, and it goes down to ground like that. That's it. I don't know if this will help any. I guess you can try to take a still picture. Oh. Like that. That's the circuit we're talking about. Not the greatest focus, not the greatest light, but hopefully if you follow along with my description, hopefully it'll all make enough sense. Okay, so that's the first problem on the test. Test 1B. That's this problem. Okay. Test 2B, or 1B, problem 2, I should say. Yours is a summing amplifier. Same type of problem, except this is with a summing amp. And I'll show you what I'm talking about in this one, that we could use a summing amp or a difference amp, because I'm going to make the gain negative. I'm going to pick data points that make it negative. You're not supposed to have that option when you take a test. It's either negative or positive. The data points that we gave were minus 1 and 4.4 again, and 1 and 1.8, and 2 and 11. And we're going to mix the 2 and the 11. And this is the in, this is the out, in volts, like that. Yeah, it's coming through okay. And so the point here is that if we draw this line, we have negative 1 here, we have positive 1 there. At negative 1, we had 4.4 volts. At positive 1, we had 1.8 somewhere along this line. So we have a negative slope here. We have a slope and we have an offset for that matter. And that's the relationship that we're trying to realize with our circuit. So once again, I dropped off the last 2 data points. Why? Just to reiterate, because it was a screw up. The last 2 data points shouldn't have been there for this problem. So given a set of reasonable data points, that your instructors won't make a mistake on the test again. So let's go ahead and figure out our gain and our offset. So delta V out, delta V in. I like to draw out on top because ultimately I'm going to get delta V out over delta V in. Delta V in, I go from negative 1 up to positive 1. That's 2 volts. Delta V out, I go from 4.4 down to 1.8. So 1.8 minus 4.4 gives me, oh, wow, 2.6. Is that what I said? Oh, hey, wrong problem there. Yeah, it gives us a negative 2.6. So the gain is equal to delta V out over delta V in is equal to this stuff is equal to minus 1.3. Now notice these have units of volts. The gain is volts per volt, otherwise known as a unitless number. So now what we're saying is that V out is equal to minus 1.3 times V in plus beta, and just for kicks, I guess we'll call it alpha. How about that? Just to distinguish it from our offset in the previous problem. So now pick an input, say 1, pick an output, say 1.8. 1.8 volts is equal to minus 1.3 times 1 volt plus alpha. So alpha is equal to 1.8 plus 1.3 is equal to 3.1 volts. Double checking. Yep, I got that one right, okay. So the relationship, which is not what we're gonna make the op-amp circuit do this, but the relationship as kind of an intermediate quantity that you should understand is V out is equal to minus 1.3 times V in plus 3.1 volts. I suppose I should put in volts. Now again, we're not going to do this way. We could use an inverting amp with a gain of 1.3 or negative 1.3 if you want to call it that. But then we'd have to add 3.1 volts to it, and that's not going to happen. I suppose we could use a difference amplifier. I'll show you how that works out in just a second. Let's pursue the summing amp, okay, just to continue with this. The point here is that as a summing amp, trying to put all these steps into one, we have 1.3 times Vn plus 3.1 divided by minus 1.3. And that's volts per volt, I guess. Yeah, I suppose I should say. That's not volts per volt, it's volts. Okay, so we could make it, and we will actually make it as 1 minus 1.3 times Vn plus a minus, and what did I come up with? 2.3846. .1 divided by 1.3 give us negative 2.3846 volts. Just to make sure you don't think that's some bizarre smudge, let's make that a minus. And we'll put brackets around the outside. There's a parentheses, brackets, and brackets. So now it's a summing amp. It has a negative gain right there. Negative gain of 1.3 times the sum of these two voltages. Now, I said we could do this with a difference amp, and we can. The alternative approach is to take this same problem, actually, and we could actually say this is 1.3, or let's see if this is, as an alternative, we could say 1.3 times 2.3846 minus Vn. And that's going to be volts minus Vn, I suppose. Oh, rats. 3846 volts minus Vn. All right. So we have a negative 1.3 times a negative 2.3846 gives us a 1.3 times 2.3846. We have negative 1.3 times Vn. We have negative 1.3 times a negative Vn. It's the same thing. So this would be the approach to using a difference amplifier. We would create a difference amplifier with a gain of 1.3, and we would subtract the input voltage from a fixed voltage of 2.3846 volts. That's the difference amp approach. The summing amp approach is go ahead and create a summing amp with a gain of 1.3, and then add a negative 2.3846 volts to the input voltage, Vn. That's what we're going to do. Summing amps are pretty easy to build. And I'll have to check the equation sheet. I apologize if I gave you a dated schematic. I think they did on the summing amp and difference amp on that equation sheet. What we're going to do, or what I'm telling you, is the acceptable path to doing it. You can make this have some resistors going to ground on the positive side. I wouldn't. Let's go ahead and be simple. Let's make that one go to ground. We have one voltage coming in here, and it acts a lot like an inverting amp, and it's the negative 1.3. And we have another voltage coming in up here. So, I don't know, I think, yeah, I did that. I hope I did on those last problems. I put in my plus or minus 12 volts, like that. Let's go ahead and bring our input voltage right here. Vn plus minus, and hook that to ground like that. We'll call this R right here, and we'll call this one 1.3 R. We could make R is equal to 10 kiloohms, in which case 1.3 R is equal to 13 kilo ohms, which incidentally would be 10 kilo ohms in series with 3 1 kilo ohm resistors. It's not the fanciest way to do it, but it works. We got 1K, 1K, 1K. And yeah, I know. Pretend you can see under the glare of that light. A 10K resistor in series with a 1K and another 1K and another 1K, all in series, so a chain of 4 resistors there. That's what we could use for this R2. This would be R2, and this would be R1, and over here we have R1. Now, pretty much we've got the 1.3 times the V in, and we've got the plus part. Now we just need to provide a negative 2.3846 volts. Same as before. Take a potentiometer, hook it to minus 12 volts, and then say that you get minus 2.3846 volts out. We're going to put that into a load follower, minus, plus, bring that out to here. That's going to go up there. On the top of the load follower, plus 12 volts. On the bottom, we have minus 12 volts. The input does not go to the ground on the load follower. Had a bunch of those on the first test that were graded like that. Finally, we have, they weren't graded like that, they were submitted, I guess I should say. There we go. We out. That's problem number 2. Okay. Any questions? That was, I know, geek humor. And by the way, there you go. That's the whole system that we've been looking at. Okay. They say the camera adds 10 pounds, right? Yeah, in my case, what is it? More like 60? All right. It's all the camera's fault. Yeah. All right, next problem. Problem number 3. Ooh, fun stuff. D to A, A to D. Actually, mostly A to D, I suppose. We got a question 3, 10 points. What range of input voltages corresponds to a digital value of 546 for a 10-bit bipolar plus or minus 10 volts A to D converter? Plus or minus 10 volt ADC, which implies a 20 volt range, right? Plus or minus 10 volts gives you 20 volt range. It is a 10-bit converter. 10 bits implies 2 to the 10 is equal to 1024. We might call them bins. It's not bits, but it's little bins that you can 1024 possible numbers that you can represent. That's really what it means. Maybe I'll even say that. 1024 possible numbers. All right, so our actual number was a digital 546. So we had 546 was the value out of a possible 1024. In other words, we're a little over halfway through the range. If we were halfway through the range, we'd be at 5 of 12. So we're more than halfway through the range. We multiply that times 20 volts, that's the range, and then we add the negative 10 volts to that. Because if you wanted to look at it, I think of it visually, here's 0, here's minus 20 volts, and here, minus 10 volts, my mistake, minus 10 volts, and up here we have 10 volts, plus, okay? And also up here we have 1023 technically, and down here we have 0, 0 base 10, 1023 base 10. So if we're at 546, this would be 512, so we're somewhere in this vicinity. It's going to be 546 base 10. Is going to be the value that we get. If we run through the numbers on all this stuff, what you'll get is this is actually equal to 0.66400625 volts. Do you really need to carry it out to 6, 7 decimal places? Probably not, but it doesn't hurt either for now. So let's suppose that we do that, okay? This is the nominal voltage. Now the question is, what possible values go into that? Well, if we went down, there are two ways of looking at this. I never thought about this till today, but let's try it. Let's try something different. The next possible voltage down is 545 out of 1024, and the next possible voltage up is 547 out of 1024. So the range should be anywhere from 545.5 up to 546.5. Just for kicks and giggles. On the low end, let's just do 545.5 over 1024 times 20 plus or minus 10. That's volts, of course, is equal to V lower. And by lower, what I mean is the lower end of the range. Now, for kicks and giggles, 546, let's go 545.5, enter, 1024 divided by, and it's going to be 0.5327148, blah, 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 20 times 10.654296875 volts above the low end. So we subtract 10 volts from that, and this is equal to 0.654296875. I just did that for kicks. Now on the high end, let's see, 546.5 over 1024 times 20 plus or minus 10 is going to give you 546.5, enter, 1024 divided by 20 times 10 from that. It's going to give you 0.67382. 8125. Now, the alternative approach, the approach that I've taught all these years in class, is it's really equal to this voltage, and then we have plus or minus V resolution over 2. V resolution over 2 is going to be 20 volts divided by 1024, and all of that divided by 2. Another 20 volts divided by 2048. 20 enter, 2048 divided by 0.009765 625. All right, so this is V resolution over 2. So let's take our nominal voltage, all right, which I already calculated out, but I'll do it again. 546, enter, 10024 divided by 20 times 10 away from that. So that gives us my 0.6640625. Swap those things. I'm going to subtract this V resolution over 2 from that. And I get 0. So this is the low end. So I have V nominal minus V resolution over 2 is equal to 0.654296875 volts, and I'll bet you it's equal to that. What do you know? Those two are the same. Pardon the squiggles, but all that excitement, just couldn't contain myself. Now, if I do this resolution over 2, let's see, undo that operation. If I take my V nominal and I add V resolution over 2 to it, I add those, I have, that's nom, V nom plus V resolution over 2. Then what I will get is 0.673828125 volts, which is the same as this. So, new approach to doing that problem. Either way, doesn't matter. Conceptually, they are the same thing. I hope you understand that. I hope it makes sense to you. I really do advocate not memorizing these equations, but just figuring out how they work. It's not all that bad. It's the fractional distance that you are through the range. That's what this represents. You have to find yourself relative to the bottom end of the range, and that gives you the nominal. All right. So the next problem is a little different, a little easier actually. The next problem says, given also another A to D converter, what digital value does a particular number convert to? So that last one we said, numbers converted to 546, parts out of 1024. What was that range of numbers? This time what we're saying is Vn is equal to 1.725 volts. This is a 0 to 5 volt ADC, which means 5 volt range, duh, as they say. It is a 12-bit ADC, therefore 2 to the 12, which is equal to 4096, because 2 to the 10 is 1024, times 2 is 2048, times 2 again is 4096. Possible numbers. Okay, so this one's really quite easy. The digital value corresponding to this number is the integer. You can't do floating points. You can't have decimal numbers in that sense. You have to have whole numbers. That's what I'm trying to say. 1.725 volts over 5 volts. Okay. Times 4096. So what distance through the range are you times 4096? And the answer to that is 1.725 over 5 times 4096 is equal to the integer value of, this says INT, at least it does now, INT of 1413 base 10 is equal to, sorry, 1413.12, which is 1413 base 10. So, and does that make sense? Well, yeah, it makes a fair amount of sense. We're a little over a quarter of the way through the range. So we're something over a quarter of the way through, no, a lot more than a quarter of the way through. The possible sets of combinations, possible 4,096 possible numbers. All right. I'm waiting to hear the clapping on this. I think I'm going to forget about uncertainty with this. It's not much fun. So let's skip on uncertainty. Let's not worry about uncertainty. Let's stick to more interesting problems. Yay, it's not a final. Okay, all right. Next problem is this one. Okay, we've got some waveforms here. This is a really tough problem to do on the board, but as far as I hope to work out okay. But I got these 3 different amplifiers. And what do the 3 amplifiers do? Well, you know, I can read it off right here. This one's very obviously an inverting amplifier. We have an input resistor of 10, we have an output resistor of 20, K in both cases. So obviously it is an inverting amplifier with a gain of 2, is what I might often say. Technically the gain is -2. Okay, that's really what it does. And so the solid line here in the middle was the original signal. And so what we do is we invert it, it goes up and down, and then we amplify it by a factor of 2. So hang on just a second. Okay, we're back again. That was a spam phone call. It was Julie with Home Security Promotions. How kind of her to want to talk to me while I was doing this. All right. You know, I actually used to listen to the spiels sometimes. Now it's just a click. Oh well. We got a load follower on the next one, where, again, as I said a few moments ago, the positive input is not connected to the ground. It's just that's where the input comes in. No current nominally goes through there. In theory, no current goes through. And then the output is connected to the negative input like that. It's a load follower. The input is exactly equal to the output. Is that really the case? Well, of course not. There's always a little bit of a DC offset. You might have to trim the op amp. Know that it is possible to do that using a resistor between, I think, pin 1 to ground. No. It's a resistor. You put a potentiometer, you put the middle leg of the potentiometer on the -12 and the other two legs on the pins 1 and 5. Beyond the scope of what we've done, don't worry about it. What you need to know now is that the trace of the output is exactly the same as the trace of the input. Down here, this is a more interesting problem. We have obviously a difference amplifier because we have two different paths that were going into this circuit. Down below, we have a 1 volt, I believe. Yeah, 1 volt signal right here. There we go. And it's going through a 20K resistor there and a 30K resistor like that. So R1 is 20K, R2 is 30K. That gives us a gain of 1.5. We have then our input coming through the same ratio of resistors but going to the output. Then what this tells us is that we have 1.5 times this 1 volt input. Did I say 1.5? I meant to say 1. 1 volt input minus this other value that we have coming in. So it's 1.5 times 1 minus Vin, otherwise known as negative 1.5 minus 1.5 Vin. So what I did over here, and I know it's probably not the best of all forums to do this, but I'll try anyways. You see the dashed line here, that is the inverse by 1.5. I have a negative 1.5 times my input voltage. My input voltage is right here. It's this nice smooth line. And then I multiply by 1.5 and I invert it. So I go, whereas the input went up 2 and down 2, my output actually goes down 3 and up 3 in inverse of that. That's not the final output. That's kind of a temporary output. That's the negative 1.5 Vn. To that I have to add 1.5 volts. So I jerk the whole thing up and I'll end up with this type of a signal that comes down. We only see parts of the signal on there, and of course I'd like to be clever that way. Or I want to test your cleverness, let's put it that way. Recognizing that I don't see the whole signal, but that's okay. That's what I expect. So that's what you can expect sometimes looking on scopes. So those are the three types of circuits that I was asking on this test. Those are the three gains, or not, if you will. Those are the three outputs. The other question here was, okay, it's a 200 hertz signal, and it has an amplitude of 1 volt. Well, it goes up 2 divisions. That's the amplitude. So it's 1 volt per 2 divisions, otherwise known as a half a volt per division. That's the vertical sensitivity. In addition, it takes 2 divisions for 1 period. If you want to look at it this way, you can always say, okay, there are 5 periods to go all the way across that range. But I think it's easier to look at just one division, one set at 1 period. We know it's at 200 hertz. The period for a 200 hertz signal then is going to be 0.005 seconds. T is equal to 0.005 seconds. I think I can point that out right up in here. And so we have 0.005 seconds right there, which means one of these divisions is going to be 0.0025, half of that. Another approach was to say, okay, I got 0.5 T per division, because half a period per division, because I had 5 T for 10 divisions. 5 periods all the way across, divided by 10 divisions. 5 T is equal to 10 divisions, means that the horizontal sensitivity is 0.5 T per division. And then I found that T was 0.005 seconds, and so, again, a half of that, 0.0025 seconds per division. That's how I did it. You figure out what makes you comfortable, I guess, or what you like to do. Finally, on this last problem, it was really pretty straightforward, I think. You can download a copy of this after I post it online. I'll do that after I post the video. I gave you a schematic here. I'm just going to go through the highlights of the schematic. Not, well, maybe I'll go through all the details, we'll see. It's a summing amp up here. We have a voltage follower here, got a potentiometer and an offset. Looks pretty dang familiar. Looks like something we've been doing. So the voltage follower says, hey, look, if I'm going to bring in negative 0.0318 volts here, then I'll get negative 0.0318 volts here. The gain of the circuit is 470K divided by 10K, otherwise known as a gain of 47. So what we have then is that V out is equal to 47 times V in. Here we have the 10K and the 470K there. So again, we have a gain of 47 on our input voltage and a gain of 47 on our load follower output. So we have 47 times V in plus a negative 0.0318 volts. In other words, and also it's a gain of negative 47. In other words, it's equal to negative 47 times Vn plus 1.5 volts. When we work out the numbers on that, if we plug in 10 millivolts, and I would not encourage you to go, oh, that's 0.1 volts like I did the first time I did it, because I was wrong. It's 10 divided by 1,000, otherwise known as 0.01 volts. You multiply that by 47, and you add that to the 1.5 volt signal there. You see the negative of the negative made a positive 1.5 volts. So these are my answers as far as the output voltages. Hopefully I didn't screw it up too royally. Now, as far as the building the schematic goes, a variety of things to keep in mind here. First off, hey, I might have lost a point there. This is plus 12, that's plus 5, that's minus 12, and that's ground. I didn't label them, though. I should have labeled them, so maybe I didn't get a perfect score on this test. In addition, what else do we have? I'm going to go ahead and hook up my ground through here down to the ground rail, the second one from the bottom. I'm going to hook up my minus 12 to the very bottom. So I have minus 12 and I have ground. I'm not going to worry about the 5 volt rail. Leave that blank. 12 volts will go to the top one. This is pretty much conventional for 360. 12, 5, ground, negative 12. So we do that hookup. That's fine. Another great place to get points on op amps. Pin 4, this lower left, lower right, I guess that'd be your lower right corner. That always goes to the negative 12. This one goes to negative 12. Pin 7, because it goes 1, 2, 3, 4, 5, 6, 7 coming back, it always goes to plus 12. That one always goes to plus 12. There you go. We've got some connections there. That's great. Load follower. Take the inverting input, as shown up here, connect it to the output, which is pin 6. Inverting input is 2, goes over to 6. We got that connection. Great. We've got to have a 10K resistor going into the inverting input over there. There's a 10K resistor, and there's the inverting input over there. We have our function generator. Hook up the low side of the function generator to ground, the high side of the function generator via a 10K resistor to the inverting input on that summing amplifier. This is a summing amplifier over here. This is a load follower. And each one of these individual devices is an operational amplifier. But together, this makes a summing amp over here. Together, this makes a load follower. Load follower input, we had to hook up that potentiometer. So we draw a potentiometer across some of these breadboard pins, not along them, because these breadboard pins are in common. If you hook up a potentiometer across these, you'll just get nothing. It just gives you a big zero resistance. Now from here to there is the full width of the potentiometer. Then we have the wiper halfway in between. We hook one end up to negative 12. We hook the other up to ground, as we showed up here in the diagram. We take this middle leg, the wiper then, and bring it over to the non-inverting input of our load follower. Hope this stuff works out all right. I'm kind of scratching it up. I haven't scanned it yet. Oh well. The only other thing that I missed so far, that we pretty well covered the load follower. We need to hook this non-inverting input on the summing amplifier, operational amplifier. We hook that up to ground, as we show up here. And then finally we go with a 470K resistor all the way across from the inverting input across to the output. And finally, the output of the scope goes over there. The low end of the scope has to go to ground. And that's it. That is test 1. Thank you for watching 360 channel.